Hey everybody. Today we're talking about concavity and points of inflection. These are both second derivative concepts. Remember, the second derivative, f double prime, is just the derivative of f prime. It's the instantaneous rate of change of f prime. Now, since we often interpret f prime as being the slope of the line tangent to y equals f of x, f double prime is measuring the rate of change of that slope. For instance, if f double prime is positive, then f prime is increasing. The slope of the tangent line to the graph of y equals f of x is increasing. In a situation like that, when f double prime is greater than 0 on an interval, we say the graph is concave up there. Roughly speaking, the graph is going to look like the bottom of a valley. On the other hand, if f double prime is negative, then f prime is decreasing. The slope of the tangent line to y equals f of x is decreasing. When that's the case on an entire interval, we say the graph is concave down there. And in a situation like that, the graph is going to look more like the top of a hill. One more definition. If f double prime changes sign at a point where f prime exists, then we say the graph has a point of inflection there. Roughly speaking, that's a place where the tangent line goes from increasing to decreasing, or vice versa, where the graph goes from looking like the bottom of a valley to the top of a hill, or vice versa. So those are the official definitions. Hopefully they're relatively clear, but I think this all really comes into focus when we start looking at pictures. So let's swap over to GeoGebra here and take a look at this graph. This is a function y equals f of x. It's defined from 0 to 2 pi. And so the x-intercepts there should be at about 3.14 and about 6.28. Incidentally, notice that in this plot, the scales for the x and y axes are not exactly the same. So I've also drawn a tangent line right near x equals 0. I've titled the x value here c. And I want to watch what happens to the slope of this tangent line as c increases. So at first, the slope of that tangent line gets smaller and smaller. And in fact, that keeps happening right up until we get to this x-intercept. The graph is concave down there. The slope of the tangent line is decreasing. The graph looks like the top of a hill. After this x-intercept, however, the slope of that tangent line is going to start increasing again. It gets bigger and bigger and bigger, all the way up until that final x-intercept at about 2 pi. The graph looks like the bottom of a valley. It's concave up in that interval. At x equals pi, right here in the middle, the tangent line is defined, and the second derivative changes from negative to positive. That is a point of inflection. Notice, by the way, that this graph can be concave down and increasing, concave down and decreasing, concave up and decreasing, concave up and increasing. So an increasing function can be concave up or concave down, as can a decreasing function. Concavity and increasing, decreasing are related concepts, but they are, in a sense, independent of one another. I think it's useful to keep the unit circle in mind. Each of the 4 quadrants shows you the behavior of a function that has a different concavity or a different increasing and decreasing characteristic. In quadrant 1, we have a graph that is decreasing and concave down, as you read from left to right. In quadrant 2, increasing and concave down. In quadrant 3, decreasing and concave up. And in quadrant 4, increasing and concave up. I think this is a very useful tool to bear in mind when we start curve sketching in particular.